Hello, my name is Callum and I'm currently a second year undergraduate student at the University of Kent. As part of my studies for the computer systems module at our university, I have made some mock questions in order to help myself like remember these concepts, core concepts about the fundamentals, the lowest layer of abstraction of how computers fundamentally work. So I'm going to be answering a few of these questions, and hopefully they will be of use, me showing my working out. So obviously we have our truth table here with the three inputs of A, B, and C, and our distinct Boolean expressions F, G, H, and J. Their definitions can be seen on the right here. For this question, let F be the result of a three-way OR gate. So in the fundamental lowest level logic gates, we have AND gates, OR gates, NOT gates. An OR gate simply means a standard OR gate has two inputs, A and B. And if any of those inputs are 1, the output will be 1. So if the input is 1 and the other input is 0, the output will be 1. If they're both 0, they will be 0. Very easy. And how does this link to a three-way OR gate? Well, a three-way OR gate is the same thing, but just with 3 inputs instead of 2. So if any one of the 3 inputs has a 1, then you know that the output will be 1. So let's quickly look through here. If all 3 inputs are 0, well, we know the output will be 0. 0, 0, 1. Well, one input is a 1, so we can fill it in with a 1. And you can go down, and all the rest of them have a 1 in them. And if they have any 1 in them, then the output will be 1. If it was an AND gate, and an AND gate requires every input to be 1 for there to be a 1, then you would have to check every single input. Just because it's got 3 inputs doesn't mean it changes in any way. Let's get rid of this. Let's go to the second question. I hope I explained that correctly. Let G be a multiplexer where A and B are its inputs and C is its select bit. So, once again, you should know from your studies or, from your notes what a multiplexer is. So, a multiplexer has 2 inputs, A and B, with a select bit on the side. In our example, this is C. And then we have an output. So what a multiplexer does is, depending on what C is, it will select which of the inputs gets outputted. So A is our input, and if 0 is in the select bit, whatever is in A's input will be outputted. So it doesn't matter. If A is 0, output will be 0. But if B is 1, it doesn't matter, because C is still 0, and it will only output what is output on A. So let's go through it. C as our select bit. This is the one we're going to be focusing on for this question. C is our select bit, which means we are outputting whatever is in A. So A, what is in A? 0. C is now 1, which means we're now selecting B. Whatever B has, we're going to put as an output. So B is 0, so we're going to put 0. C is 0 again, so we're looking at A. A is 0, so our output is still 0. Now here we go. C is now 1, which means we select B, and B is 1, so the output is 1. Once again, C is 0, A is 1, output is 1. C is 1, so B is the output. We put 0. 0, you select A is 1. 1, select B, B is 1. And that's that that question answered. That answer question, bloody hell. And then the last question. H and J to be the sum and carry bits of a 1-bit full adder, where A and B are the inputs and C is the input carry. So this is going to need a little bit more explanation. So when you add in base 2, or if you add in anything, right? Let's say we add 9 and 3. When you add them, you have a carry and the sum. So 9 and 3 is 12. So you carry the 1 over to the next unit and you leave whatever is left. It's same with binary. So in base 2 addition, if you're adding 1 and 1, that equals 2. But obviously 2 in binary is 1, 0. So you have the 1 as the carry and 0 as the sum. But in logic, how are we going to make a gate that can do that for us? So we know that if 1 and 1 are together in base 2 arithmetic, 1 will be the carry. And then in later additions, if there is another 1 and 1 to add, you have to add this one as the carry bit. So now we're adding 1, 1 and 1, which means that obviously equals 3, but 3 in binary is 1, 1. So we put the 1 in the sum and we carry the other one and it gets caught over. That's just very basic binary addition. But now, that's basically what you're doing. So when it says a full bit adder is just a little box. Let's call it full adder. And it's got 3 inputs, A, B, and C, where A and B are these first 2 numbers, and C is the carry, right? And as we discussed, if you're adding 1 and 1 with 0 as the carry bit, then it's 2, which equals 1, 0. So the sum would be 0, and the output would be 1, or the carry would be 1. And what these outputs are. This top one can be the sum, and this bottom one can be the carry. So let's go through each one of these. If we're adding 0, 0, and 0, let's write over here. 0, 0 with a carry of 0. All of it added together, you get 0, but with the carry of 0. You have to remember the carry. Because if the carry doesn't exist, obviously you wouldn't write it down, but it would still show as a 0. So we know that will be 0, 0. And now we have the carry of 1, but 0 as the adds. So if we had, 0, 0, and then the carry of 1, 0, 0 plus is 0, but you need plus 1. So 1 in the sum category, but the carry is still 0 because you're only adding 1. 1 plus 0 is 1. So we can fill that in. And we can go down the line. We are just adding these 3 numbers in binary and in representing the output in binary as well. So 0 plus 1 plus 0 is just 1. And once again, the carry bit, you have to put a 0 even though we wouldn't write it. 0 plus 1 plus 1, we have a case of a carry. So 0 plus 1 plus 1 is 2. But in binary, it is 1, 0. So the carry bit would be 1, but keyly, the sum bit would be 0. Because you're representing it in binary. So 1 plus 0 plus 0 is 1 with a 0 carry. 1 plus 0 plus 1 is 2. So the sum bit would be 0 and the carry bit would be 1. 1 plus 1 plus 0 is once again 0 and 1. And 1 plus 1 plus 1, as we did over here, equals 3. But in binary representation, the sum would be 1 and the carry would be 1. So that equates to 1, 1. And we've done it. We've completed the truth table. I hope that makes sense, and I hope that I've gone through it enough. Yeah, thank you for watching.